Welcome back to our second lesson for our course at Branding Institute of Forensics and Security. We are talking about fire safety protection, and today we shall be talking about fire chemistry. Fire chemistry. Um, they also call it fire behavior. This is actually how fire happens and how fire occurs and how fire starts. It is a lengthy presentation which will take us almost 1 hour. I try to make it lengthy to cover some of the areas so that we are not only touching on the basics. So it will take us almost 1 hour to cover this one. And I hope that we are going to start on a positive note and everybody is okay and everybody is ready to go. So to start off, fire chemistry. Actually, this involves a basic understanding of fire behavior. Basic understanding of fire behavior. To perform safety and effectively in any firefighting function, a firefighter now who is you should have a basic understanding of fire behavior, which is the science of fire and the factors that affect its ignition, growth, and speed and spread. An understanding of the fire behavior and the phases a fire passes through as it grows assists the firefighter in selecting the proper tactics to attack and extinguish fires. This knowledge also helps in recognizing potential hazards to themselves and others while they work on the fire ground. Um, as I have said, we are approaching this lesson from the perspective that you are a firefighter. We saw in the introduction that you, as the initial or first responder on the ground, responding to a fire situation, you are a firefighter. Even before you call in backup, you call in the fire brigade, you call in the assistance from the city council or the Nairobi City Fire Services or other organizations that deal with fire safety like G4S. You are the one on the ground. You are the first responder. So we are going to approach this course with the perspective that you are the firefighter. About fire. Fire has been both a help and a hindrance to mankind throughout history. Fire has heated our homes, cooked our food, and helped us to become technologically advanced. Fire, in its hostile mode, has also endangered us for as long as we have used it. Technically, fire is a chemical reaction that requires fuel, oxygen, and heat to occur. Fuel, oxygen, and heat to occur. Over the last 30 years, scientists and engineers have learned a vast amount about fire and its behavior. So fire has been both a help and a hindrance to mankind throughout history. Temperature and heat transmission. Anyone who has ever participated in or even watched firefighting operation knows that a fire can generate tremendous amount of heat. Heat is the energy transferred from one body to another when the temperatures of the bodies are different. Heat is the most common form of energy encountered on Earth. Temperature is an indicator of heat and is the measure of the warmth or coldness of an object based on a particular standard. In most cases today, the standard is based on the freezing and boiling points of water. Freezing point being 32 degrees Fahrenheit or 0 degrees centigrade, and boiling point being 212 degrees Fahrenheit or 100 degrees centigrade. Keep those figures in mind and also do more research on them. Freezing 32 degrees Fahrenheit or 0 degrees centigrade, and boiling 212 degrees Fahrenheit or 100 degrees centigrade of water. Temperature is measured using degree Fahrenheit in the customary system, that is in English. and degrees Celsius in the International System of Units. The transfer of heat from the first fuels ignited to other fuels and in beyond the area of fire origin controls the growth of any fire. Firefighters should use their knowledge of heat transfer to estimate the size of a fire before attacking it and to evaluate the effectiveness of an attack. You can just estimate the size of a fire by attacking it and evaluating the effectiveness of an attack. You should use your knowledge of heat transfer to estimate the size of a fire before attacking it. If a fire is producing more heat than the firefighters can safely overcome, then they should remove themselves from immediate area and call for additional resources or wait for the outside agencies, fire and emergency services organizations to respond. Heat can be transferred from one body to another by three mechanisms. Heat can be transferred from one body to another by three mechanisms, and that is conduction, convection, and radiation. So heat can be transferred from one body to another by three mechanisms, which are conduction, convection, and radiation. So from the figure that is on this slide, you can basically see convection, you can basically see conduction, and you can basically see radiation. We are going to look at them separately and to better understand these concepts. Conduction. Conduction is the point-to-point transmission of heat energy. Conduction occurs when a body is heated as a result of direct contact with a heat source. In general, heat transfer early in the development of all fires is almost entirely due to conduction. Later, as the fire grows, hot gases begin to flow over objects some distance away from the point of ignition, and conduction again becomes a factor as the heat from the gases is transferred to structural components or other fuel packages. I'll send you the notes. I'll send you the direct notes that I'm using for this presentation, so you can read also on your own. You read also on your own, and you try to keep this in your mind, because for you to be effective in fighting fire, we say you have to be able to estimate the amount of heat that the fire is generating. Heat insulation is closely related to conduction. Insulating materials do their job primarily by slowing the conduction of heat between two bodies. Good insulators are materials that do not conduct heat well because of their physical makeup and thus disrupt the point-to-point transfer of heat energy. The best commercial insulators used in building construction are those made of fine particles or fibers with void spaces between them, filled with a gas such as air. So you can also see a figure there and some photo that illustrates more on conduction. Convection. As a fire begins to grow, the air around it is heated by conduction. The hot air and products of combustion rise. Heat can be conducted through walls by direct contact with pipes or ducts. Hold your hand over a flame, you are able to feel the heat, even though your hand is not in direct contact with the flame. The heat is being transferred to your hand by convection. Therefore, convection is the transfer of heat energy by the movement of heated liquids or gases. When heat is transferred by convection, there is movement or circulation of a fluid, any substance, liquid or gas, that will flow from one place to another. As with all heat transfer, the flow of heat is from the warmer areas to the cooler areas. That is convection. You can see figures to illustrate convection. I will give you 1 minute to have a look at them and to try to figure out, try to put into your mind what we are talking about. saw convention within a room, you can see exactly how the heat is transferred from the heated source to other areas. These are fluids or gases. Radiation. If you hold your hand a few inches, millimeters, to the side of the small fire used as an example, you'd also be able to feel heat. This heat reaches your hand by radiation. Radiation is the transmission or transfer of heat energy from one body to another body at a lower temperature through intervening space by electromagnetic waves. All warm objects radiate heat. The best example of heat transfer by radiation is the sun's heat. So radiation is actually the transfer of heat energy from one body to another at a lower temperature through intervening space by electromagnetic waves. The energy travels at the speed of light from the sun through space, a vacuum, and warms the Earth's surface. As a fire grows, it radiates more and more energy in the form of heat. In large fires, it is possible for the radiated heat to ignite buildings or other fuel packages some distance. You can also see an illustration of radiation of heat from the sun through rays. In large fires, it is possible for the radiated heat to ignite buildings or other fuel packages some distance away. Combustion, fire, and combustion. Now here we are talking about two words. We are talking about combustion, fire, and combustion. Combustion, fire, and combustion are terms that are often used interchangeably. Technically, however, fire is a form of combustion. We talk about combustion, fire, and combustion. These are generally terms that are used interchangeably, but fire is a form of combustion. Combustion is a self-sustaining chemical reaction yielding energy or products that cause further reactions of the same kind. Fire is a rapid self-sustaining oxidation process accompanied by the evolution of heat and light of varying intensities. The time it takes a reaction to occur determines the type of reaction that is observed. At the very slow end of time spectrum is oxidation, where the reaction is too gradual to be observed. At the faster end of the spectrum are explosions that result from the very rapid reaction of a fuel and an oxidizer. These reactions release large amount of energy over a very short time. For combustion to occur, four components are necessary. Combustion is burning. Fuel, which is the oxidizing agent. Oxygen, which is the oxidizing agent. Fuel, heat, and self-sustained chemical reaction. This is what we call the fire tetrahedron. Initially, we only used to refer to the fire triangle, where we used to speak of fuel, heat, and oxygen. But now we look at it in a different perspective, where we look at a chemical chain reaction, which is a fire tetrahedron. You can see from the picture on this slide that we have oxygen, and we have fuel, and we have heat, and then all this combined together leads to combustion. These components can be graphically described as the fire tetrahedron. Each component of the tetrahedron must be in place for combustion to occur. If we bring these things together, then definitely fire will occur. So in simple terms, if you are asked to say something about the fire triangle, you talk about oxygen, you talk about fuel, you talk about heat, and you mention that when we bring this together, then definitely fire will occur. Take note, in most interviews, when we interview security officers or security managers, we want to know if they have basic knowledge of fire, because the basic knowledge of fire is very important to the successful safeguarding of people and assets. So we want to know if people have basic knowledge of first aid, basic knowledge of fire, basic knowledge of CCTV surveillance, basic knowledge of risk, basic knowledge of investigation, basic knowledge of occupational health and safety standards or measures or requirements. Act 2007 of the Kenya laws. So these are some of the very important things that you have to focus on as a security manager as you grow in your career. Not forgetting information security. Information security. This concept is extremely important to students of fire, suppression, prevention, and investigation. Remove any one of the four components and combustion will not occur. If oxygen has already occurred, if ignition has already occurred, the fire is extinguished when one of the components is removed from the reaction. To better explain of fire and its behavior, each of the following components of tetrahedron is discussed in the following slides. So in the following slides, we are going to discuss these components in detail. So let's start with oxygen. The oxygen in air around us is considered the primary oxidizing agent. Normally, air consists of about 21% oxygen. At room temperature, which is 70 degrees for 21 degrees Celsius, combustion is supported at oxygen concentrations as low as 14%. When oxygen concentration exceeds 21%, the atmosphere is said to be oxygen enriched. Under these conditions, materials exhibit very different burning characteristics. Materials that burn at normal oxygen level burn more rapidly in oxygen-enriched atmosphere and may ignite much easier than normal. So when we supply more oxygen near materials that burn at normal oxygen levels, then they will burn more readily. Some petroleum-based materials will auto-ignite in oxygen-enriched atmospheres. Can you think about that? That some petroleum-based materials will auto-ignite in oxygen-enriched atmospheres. Many materials that do not burn at normal oxygen levels burn readily in oxygen-enriched atmospheres. My fellow professionals, my fellow security people, I want you to think about these things. I want you to think about these concepts. I want you to research more about these concepts. Fuel. Fuel is the material or substance being oxidized or burned in the combustion process. That is why when we say we remove fuel, for example, if it is wood, the 3 stones we use at home in Kenya, and we put firewood below and it's burning, if we remove the wood, this is the fuel. When we remove the wood, we are removing the fuel. Fuel is the material or substance being oxidized or burned in the combustion process. Fuel may be found in any of 3 states of matter: solid, liquid, or gas. Most common fuels contain carbon along with combinations of hydrogen and oxygen. These fuels can be further broken down into hydrocarbon-based fuels such as gasoline, fuel oil, and plastics, and cellulose-based materials such as wood and paper. Other fuels that are less complex in their chemical makeup include hydrogen gas and combustible metals such as magnesium and sodium. The combustion process involves 2 key fuel-related factors: the physical state of the fuel and its distribution. So, fuel. And then from the earlier discussion on matter, a fuel may be found in any of 3 states of matter: solid, liquid, or gas. To burn, however, fuels must normally be in the gaseous state for solids and liquids. Energy must be expended to cause these state changes. Fuel gases are evolved from solid fuels by pyrolysis. Pyrolysis is the chemical decomposition of a substance through the action of heat. Simply stated, or as solids fuels are heated, combustible materials are driven from the substance. If there is sufficient fuel and heat, the process of pyrolysis generates enough burnable gases to ignite if the other elements of fire tetrahedron are present. Turning our attention to still concentrating on the fuel. Because of their nature, solid fuels have a definite shape and size. This property significantly affects their ease of ignition. Of primary consideration is the surface to mass ratio of fuel. The surface to mass ratio is the surface area of the fuel in proportion to the mass. One of the best examples of the surface to mass ratio is wood. To produce usable materials, a tree must be cut into a log. The mass of this log is very high, but the surface area is relatively low. Thus, the surface to mass ratio is low. The log is then milled into boards. The result of this process is to reduce the mass of the individual boards as compared to the log, but the resulting surface area is increased, thus increasing the surface to mass ratio. These are a little bit complex areas of thinking, but I am introducing them so that we may move into the right direction and we may understand how to effectively control and how to effectively prevent fire. It doesn't make any sense just to talk about the three elements, to talk about fuel, heat, and gas, fuel, heat, and oxygen without going a little bit into the details to make us better understand what we are talking about. So move with me as we go along. The sawdust that is produced as the lumber is milled has an even higher surface to mass ratio. If the boards are sanded, the resulting dust has the highest surface to mass ratio of any other examples. As this ratio increases, the fuel particles become smaller, more finely divided. For example, sawdust as opposed to logs, and their ignitability increases tremendously. Just imagine sawdust, how it can easily ignite compared to a mass of log. As the surface area increases, more of the material is exposed to the heat and hence generates more burnable gases due to pyrolysis. A solid fuel's actual position also affects the way it burns. If the solid fuel is in a vertical position, fire spread will be more rapid than if it is in a horizontal position. So keep in mind, structural buildings that are in a vertical position will burn more rapidly. The fire will grow more rapidly compared to structures that are in a horizontal position. For example, if you were to ignite a sheet of 1/8-inch plywood paneling that was lying horizontally on two sawhorses, the fire would consume the fuel at a relatively slow rate. The same type of paneling in the vertical position burns much more rapidly. The rapidity of the fire spread is due to increased heat transfer through convection as well as conduction and radiation. For liquids, fuel gases are generated by a process called vaporization. In scientific terms, vaporization is the transformation of a liquid to its vapor as gaseous or state. Vaporization is the transformation of a liquid to its vapor or gaseous state. Vaporization. The transformation from liquid to vapor or gas occurs as molecules of the substance escape from the liquid surface into the surrounding atmosphere. In order for the molecules to break free of the liquid surface, there must be some energy input. In most cases, this energy is provided in the form of heat. For example, water left in a pan eventually evaporates. The energy required for this process comes from the sun or surrounding environment. Water in the same pan placed on a stove and heated to boiling vaporizes much more rapidly because there is more energy being applied to the system. The rate of vaporization is determined by the substance and the amount of heat energy applied to it. Vaporization of liquid fuel generally requires less energy input than does pyrolysis for solid fuels. I think that is self-explanatory. If you put water on a pan and you place it outside on the sun, it will take a longer time to vaporize compared to when you put it on a cooking stove and then you put fire underneath. So vaporization of liquid fuel generally requires less energy input than does pyrolysis for solid liquids. This is primarily caused by the different densities of substances in solid and liquid states, and by the fact that molecules of a substance in the liquid state have more energy than when they are in the solid state. Solids also absorb more of the energy because of their mass. The vitality or ease with which a liquid gives off vapor influences its ignitability. All liquids give off vapors to a greater or lesser degree in the form of simple vaporization. Liquids that easily give off quantities of flammable or combustible vapors can be dangerous. Like the surface to mass ratio for solid fuels, the surface to volume ratio of liquids is an important factor in their ignitability. A liquid assumes the same shape of its container. Thus, when a spill or release occurs, the liquid assumes the shape of the ground, flat, flows and accumulates in low areas. When contained in the specific volume of a liquid, has a relatively low surface to volume ratio. When it is released, this ratio increases significantly, as does the amount of fuel vaporized from the surface. Gaseous fuels can be the most dangerous of all fuel types because they are already in the natural state required for ignition. So we say gaseous fuels are the most dangerous of all fuel types because they are already in the natural state required for ignition. No pyrolysis or vaporization is needed to ready the fuel, and less energy is required for ignition. Let us continue with this trying to understand these things. For combustion to occur after a fuel has been converted into a gaseous state, it must be mixed with air oxidizer in the proper ratio. The range of concentration of the fuel vapor and air oxidizer is called the flammable explosive range. The flammable range of a fuel is reported using percentage by volume or gas or vapor in air for the lower flammable limit and for the upper flammable limit. The lower flammable limit is the minimum concentration of fuel vapor and air that supports combustion. Concentrations that are below the LFL are said to be too lean to burn. The upper flammable limit is the concentration above which combustion cannot take place. Concentrations that are above this are said to be too rich to burn. It is often helpful for firefighters to identify groups of fuels or fuel packages in an area or burning compartment. These fuel packages may include the following: fuel systems, oil, and natural gas; atomized fuel systems; pulverized coal systems; housekeeping hazards; accumulation of improperly stored hazardous materials; accumulation of improperly stored hazardous materials. Note: leaks in fuel systems can cause hazardous accumulations within pipes that are routed through improperly vented spaces or walls. Some fuel system leaks are visible. However, others may not be seen or noticed because of plant noises. In outside areas, fuel packages could be clusters of underbrush or trees growing closer together. In an outside storage area, a fuel package might be a tank of fuel or flammable liquid or a pile of lumber or building materials. The total amount of mass of fuel in a compartment or specific location multiplied by the heat of combustion of the materials is called the fuel load or the fire load. the fuel load, or the fire load. The term commonly used to describe the minimum heat that would be released if all the materials in an area are or compartment burned. The concept of fire load was the basis for many of the fire resistance requirements found in today's building codes. Remember, we are going to look at building codes also in this course. Fire loading is normally expressed in terms of the heat of combustion of wood. Materials with different heats of combustion are converted to be equivalent to wood. The available fuels in a space and the proximity of fuel packages to each other have significant impact on the growth and development of fires. As the amount of available fuel increases, the potential heat releases rate of a fire in the compartment increases. If fuel packages are very close together, the amount of energy required for fire in one package to generate enough heat to ignite the nearby target fuel is less than that for the target packages at greater distance. Fuel load. Heat. Heat is the energy component of the fire tetrahedron. When heat comes into contact with the fuel, the energy supports the combustion reaction in the following ways: causes the pyrolysis of solid fuels or vaporization of liquid fuels and the production of ignitable vapors or gases, provides the energy necessary for ignition, causes the continuous production and ignition of fuel vapors or gases so that the combustion reaction can continue. Most energy types produce heat. For our discussion of fire and its behaviors, however, chemical, electrical, and mechanical energy are the most common sources of heat that result in the ignition of fuel. So, chemical, electrical, and mechanical energy are the most common sources of heat that result in the ignition of fuel. Self-sustained chemical reaction. Combustion is a complex reaction that requires a fuel in the gaseous or vapor state, an oxidizer, and heat energy to come together in a very specific way. As you have seen, it is a complex process, and I went into those few details to give you a hint into what you need to know as a security officer or as a firefighter as you grow in your career. I will also send you the notes with those details so that you read them and you try to understand them and to make sense of what we are talking about. Once flaming combustion or fire occurs, it can only continue when enough heat energy is produced to cause continued development of fuel vapors or gases. Scientists call this type of reaction a chain reaction. A chain reaction is a series of reactions that occur in sequence with the results of an individual reaction being added to the rest. For example, if you continue to add wood, fire that is already burning, and you continue to add food, then the fire will continue to grow in its development. An example of a chemical chain reaction is a forest fire. The heat from one tree may initiate the reaction burning of a second tree, which in turn ignites a third, and so on and so on. The fire will then go on at a steady rate, but if one burning tree ignites, say, two others, and each of these two ignites two more for a total of 4, and so on, the rate of burning speed rapidly increases. The self-sustained chemical reaction and the related rapid growth are the factors that separate fire from slower oxidation reactions. Slow oxidation reactions do not produce heat fast enough to reach ignition, and they never generate sufficient heat to become self-sustained. Examples of slow oxidation are the rusting of iron and the yellowing of paper. Examples of slow oxidation. Check on that one also, the research on that area also. Slow oxidation reactions. Fire development. When the 4 components of the fire tetrahedron come together, ignition occurs. For a fire to grow beyond the first material ignited, heat must be transmitted beyond the first material to additional fuel packages. In early development of a fire, heat rises and forms a plume of hot gases. If the fire is in the open, outside or in a building, the fire plume rises unobstructed and air is drawn into it as it rises. Because the air being pulled into the plume is cooler than the fire gases, this action has a cooling effect on the gases above the fire. The spread of fire in an open area is primarily due to heat energy that is transmitted from the plume to nearby fuels. The spread of fire in an open area is primarily due to the heat energy that is transferred from the plume to nearby fuels. The development of fires in a compartment is more complex than those in the open. For the purpose of this discussion, a compartment is an enclosed room or space within a building. The term compartment fire is defined as a fire that occurs within such a space. Fire that occurs within a compartment or a building inside. The growth and development of a compartment fire is usually controlled by availability of fuel and oxygen, the material and oxygen. That is why we usually say close windows and doors when moving out to cut off supply of oxygen. When the amount of fuel available to burn is limited, the fire is said to be fuel controlled. When the amount of available oxygen is limited, the condition is said to be ventilation controlled. So remember, fuel controlled, amount of fuel is limited. Ventilation controlled, amount of oxygen is limited. Recently, researchers have attempted to describe compartment fires in terms of stages or phases that occur as the fire develops. These stages are as follows: ignition, growth, flashover, fully developed, and decay. You can see from the photo diagram. I'll give you a few minutes, 1 minute, just to have a look at it. Fire development: ignition, growth, flashover, fully developed, and decay. And we shall look at them separately, quickly, in the interest of time. So 1 minute. Ignition describes the period when the four elements of the fire tetrahedron come together and combustion begins. The physical act of ignition can be piloted, caused by a spark or flame, or non-piloted, caused when a material reaches its ignition temperature as a result of self-heating, such as spontaneous ignition. At this point, the fire is small and generally confined to the material fuel first ignited. So at this point, you can be able to extinguish the fire. That is, if you are alert enough, if you conduct thorough patrols, if you are at the location at that particular time, then you can be able to extinguish this fire at this point. Growth. Shortly after ignition, a fire begins to form above the burning fuel. As the palm develops, it begins to draw or entrain air from the surrounding space into the column. The initial growth is similar to that of an outside unconfined fire, with the growth a function of the fuel first ignited. Unlike unconfined fire, however, the plume in a compartment is rapidly affected by the ceiling and walls of the space. The first impact is the amount of air that is entered into the plume. Because the air is cooler than the hot gases generated by the fire, the air has a cooling effect on the temperatures within the plume. The location of the fuel package in relation to the compartment walls determines the amount of cooling that takes place. Fuel packages near walls entrain less air and thus have higher plume temperatures. Fuel packages in containers entrain less air and have the highest plume temperatures. This factor significantly affects the temperature in the developing hot gases layer above the fire. The growth stage will continue if enough fuel and oxygen are available. Compartment fires in growth stages are fuel controlled. As the fire grows, the overall temperature in the compartment increases, as does the temperature of the gas layer of the ceiling level. This is fire growth. So ignition, the stages, we say compartment fire: ignition, then growth, then we move to the flashover. So we start with ignition, early stages, growth, and then flashover. A flashover is the transition between the growth and the fully developed fire stages, and is not a specific event such as ignition. During flashover, conditions in the compartment change very rapidly as the fire changes from one that is dominated by the burning of the materials first ignited to one that involves all of the exposed combustible surfaces within the compartment. Radiant heating causes paralysis in the combustible materials in the compartment. The gases generated during this time are heated to their ignition temperature by radiant energy from the gas layer of the ceiling. While scientists define flashover in many ways, most base their definition on the temperature in a compartment that results in the simultaneous ignition of all the combustible contents in space. While no exact temperature is associated with this occurrence, a range from approximately 900 degrees Fahrenheit to 1200 degrees Fahrenheit, which is 483 degrees Celsius to 649 degrees Celsius, is widely used. This range correlates with the ignition temperature on carbon monoxide, which is 1128 degrees Fahrenheit or 609 degrees Celsius, one of the most gases given off from paralysis. Just prior to flashover, several things are happening within the burning compartment. The temperatures are rapidly increasing, additional fuel packages are becoming involved, and the fuel packages in the compartment are giving off combustible gases as a result of paralysis. As flashover occurs, the combustible materials in the compartment and the gases given off from paralysis ignite. The result is a full room involvement. At this stage, you should not move closer to this situation if you are not wearing what we call a fireman's gear, a fireman's suit, fireman helmet, a breathing apparatus, and you are holding a hydrant or other extinguishing agent. At this stage, you cannot use a fire extinguisher. The heat release from a developed room at flashover can be on the order of 1,000 kilowatts or more. Industrial fire brigade members who find themselves in a compartment flashover are at extreme risk, even while wearing their personal protective equipment. At flashover, the risk is very high. What you can do, you can see the status of the fire visibly, and the only thing I would advise you to do is to evacuate from the scene immediately. To evacuate from the scene is to move from the risk zone to a safer zone immediately without any further delay. Fully developed. The fully developed fire stage occurs when all combustible materials in the compartment are involved in the fire. Let's go back to a little bit. Fully developed. The fully developed stage occurs when all combustible materials in the compartment are involved in fire. Everything is burning now. Everything is burning. During this period of time, the burning fuels in the compartment are releasing the maximum amount of heat possible for the available fuel packages and producing large volumes of gases. The heat released and the volume of fire gases produced depends on the number and size of the ventilation openings in the compartment. The fire frequently becomes ventilation controlled, and hence large volumes of unburned fire gases are likely to begin flowing from the compartment of origin into adjacent spaces or compartments. These gases ignite as they enter a space where air is more abundant. That is now fully developed. From the fully developed stage, the fire will go to decay. Decay, as the fire consumes the available fuel in the compartment, the rate of heat release begins to decline, because now the material is the fuel is has consumed the material. We are not adding more materials. Materials that were present have all been consumed by the fire, so the rate of heat release begins to decline. Once again, the fire becomes fuel controlled. The amount of fire diminishes, and the temperature within the compartment begins to decline. The remaining mass of glowing ambers can, however, result in moderately high temperatures in the compartment for some time. Factors that affect fire development. So remember, there is ignition, there is growth, there is a flashover, and then there is a decay. Ignition, fire development. Ignition, growth, flashover, and then decay. We can be able to only extinguish these fires in the initial stages of ignition. That is when we can use a fire extinguisher. When it comes to flashover, then we growth and flashover, we may need advanced firefighting systems that we are going to talk about: fire suppression systems, fire engines, and other things that are required, or other systems that are required to extinguish fires in this stage. Now, there are some factors quickly that affect the fire development, and these factors are: as the fire progresses, several factors affect its behavior and development within the compartment: size, number, and arrangement of ventilation openings, volume of the compartment, thermal properties of the compartment enclosures, ceiling height of the compartment, size, composition, and location of the fuel package that is first ignited, availability and locations of additional fuel packages, and then also other factors. For a fire to develop, enough air to support burning beyond the ignition stage must be available. The size and number of ventilation openings in a compartment determine how the fire develops within space. The temperatures that develop in a burning compartment are the direct result of the energy released as the fuel burn. Because matter and energy are conserved, any loss in mass caused by a fuel fire is converted to energy. In a fire, the resulting energy is in the form of heat and light. The amount of heat energy released over time in a fire is called the heat release rate. The heat release rate is directly related to the amount of fuel being consumed over time, and the heat of combustion, the amount of heat specific mass of a substance gives off when burning, of the fuel being burned. We have come to the end, by the way, of this presentation. I knew it will take 1 hour. Now it has taken us almost 48 minutes, because I knew this was the longest presentation in this course, that is fire safety and prevention. This stage is very important for you to understand the basics. So when we move to the next lessons, when we move to basic fire prevention, first, before we go to basic fire prevention, I think we are going to study the basic fire hazards identification, and then we shall go to basic fire prevention, fire control and extinguishing, and then we shall go to strategies used in fighting fire, and then we shall also look at case studies, as I said earlier. So I was trying to develop from the introduction part of it, and then now we come to the fire chemistry, fire behavior, which is a very complex topics. I'll send you the notes. You read more in detail. You understand how these things work. Specifically, the fire tetrahedron. You think about the fuel. You think about more about the heat. You think about more about the oxygen, and you think about the combustion in general. I want to say thank you very much, and we shall continue to our third lesson this coming weekend. So thank you very much, and I wish you the best of everything. Bye bye.